right, let's go ahead and get started on this review. Question number 1, if P of t is the size of population at time t, which of the following differential equations describes linear growth in the size of the population? So again, if population is growing linearly, okay, so that's P, then the derivative would have to be a constant. And the only one that is a constant is letter A. That's it for number 1. Number 2, at time t is greater than or equal to 0, a cube has a volume v of t and edges of length x of t. So volume is going to be, of a cube, it's just the whatever the edge is cubed. If you're unsure, it's just length times width times height. And if they're all the same, it's going to be x times x times x or x cubed. If the volume of the cube decreases at a rate, so because it's decreasing, we know dv dt is going to be negative at a rate proportional. That means we're going to have a k value here, some constant, to its surface area. Now, surface area of a cube has 6 surfaces, all the same, so it's going to be 6, and each surface is a square of area x squared. So it's going to be negative k times 6x squared. So I'm looking for a differential equation, a dv dt, that has an x squared in it. That eliminates b, that eliminates c, that eliminates d, and sure enough, A is the only one. Number 3, the population of a city grows according to the differential equation dB dt equals Kp, where K is a constant, T is measured in years. If the population of the city doubles every 12 years, this is that growth factor on the very last page of the notes that we went over. Sorry, it doubles. That's the growth factor. I apologize for that. That's the growth factor right there. And 12 years is the time. What is the value of K? And so we said that K is going to be the ln of the growth factor divided by 12, the time. So it's going to be the ln of 2 over 12, and the ln of 2 over 12 works out to be 0.058. Which of the following is the solution to the differential equation that dy dx equals e to the y plus x with an initial condition of y of 0 is equal to the negative ln of 4? So the first thing you have to do is we need to understand that that function can be split as, and if we go back to the very definition of the process of solving a differential equations, we want it as a product of a function of x and a function of y. So we can write this one here as e to the y times e to the x. So now I can divide by e to the y equals, sorry, the dy should be there, multiply by dx, I get e to the x dx. So I'm going to rewrite this as e to the negative y dy equals e to the x dx, and we're going to integrate. Now the problem is this, the right side works out nice and easy. The integral of e to the x is e to the x plus c. On the left side, we have an issue in that that exponent is a function. So therefore, I need the derivative of that in my problem in order to do anything. So that means I need to put in here a factor of -1. That's the derivative of negative y. And we balance it by putting a -1 on the outside. So now I get negative from the -1, and this is just a function of e, so we get e to the negative y. Again, if you're a little unsure about that, go ahead and derive this and see that we do get back e to the negative y. So let's go ahead and put in 0 for x and the negative ln of 4 for y. So on the right side, e to the 0 is 1 plus c. On the left side, the opposite of negative ln of 4 would be positive ln of 4. E to the ln of 4 is just 4, and so we get that, -4. Taking away 1 gives me a constant of -5. So I'm going to now come over here. That leaves me a function now, negative e to the negative y equals e to the x minus 5. Go ahead and multiply through by -1. That has the effect of just swapping the order of these. It's going to make the e to the x negative and the 5 positive. Now we're going to go ahead and take the ln of both sides. And then we negate it. So y is equal to the negative ln of 5 minus e to the x, or leaving the e to the x as negative and then putting the plus 5 after would give us answer C. And we'll continue in the next video with numbers 5, 6, and 7.